Thank you again for this opportunity to speak. As some of you know, I have come here for a 1-month research visit, so I'm available for further discussion. I thought I would give a talk initially about some of our work, and I hope this might stimulate some follow-up discussions. So I'll be here all through this month. My talk today is about 5G network architecture and the future mobile internet. We have been working for the past about 5 years now to work on a clean slate architecture for the internet, taking into account future requirements. So I'll discuss that. But before I do that, let me say a few words about Winlab and where I'm from. So just to give you a little background about our lab, Winlab has been in operation since about 1989. So we're approaching 30 years now. It started before digital cellular. And the very first projects were on CDMA and 3G and so on. And over the years, wireless and networking have both evolved, and we have tried to stay abreast with many of the current trends. Giovanni has worked with us in the past, and we have done some things together. So we also have various European collaborations currently going on. But just to give you a snapshot about some of our the research projects that we do, and before that mentioning that we have about 25 faculty and staff in Winlab, and they're working on a wide range of topics which go from information theory to wireless technology and mobile networks and computing. And here are just some examples of some of the projects that are currently going on. We have a large group of projects in the area of spectrum, and there are many approaches to that: spectrum sensing, avoidance, cooperation. This particular diagram shows an example of two networks which cooperate through network interfaces, and in that way can improve the dense spectrum usage significantly. I'll be talking today about the second project, which is on future internet architecture, and that's the MobilityFirst project, which I'll again get into details. We have some emerging projects on edge cloud type of technology, where the idea is that in an edge cloud scenario, you have a number of mobile devices which are migrating. There can be hotspots of traffic, and all of them require some kind of computing service. So how do you maintain a smooth and continuous computing in that environment? A related thing is that of connected vehicles, where you can think about connected cars being able to cooperate when they're on the roadway. This diagram just shows an example of if I have a view from my car and there's a car 100 feet ahead which has a different view, they can combine their images and come up with a better global picture of the roadway around them. So that's an example of cooperative processing between cars. And one of my colleagues, Marco Gruteser, has been working very actively with several car companies, and is again something Giovanni knows a lot about. Okay, so a big part of Winlab has also been that we tend to put everything into a research prototype. And to do that, instead of building many independent prototypes, we have invested heavily towards building general purpose laboratories, which can then be used to do different kinds of experiments. So we started out with a lot of work on software-defined radio that dates back to mid-90s. And since then, we have evolved to build all kinds of devices. This is a SDR unit, which is in this yellow orbit box, which has a number of components over here. But just to keep it simple, this can realize any base station now. Pretty much LTE and various kinds of experimental systems can be built using this platform. This is a small device that we made for IoT. This is a massive MIMO rack, which is available in the Orbit testbed. The Orbit testbed itself is an interesting thing that we started building about 10 years ago, and it's been in operation since then. It gives you access to hundreds of radio nodes, fully programmable, and most of them are software-defined radios. Previously, we started out with hardware-based Wi-Fi and so on. As the technology improved, we've made all these radios. So what's interesting here is they're arrayed as a grid on the ceiling of an enclosed room. And this allows you to set up any kind of topology and to create dense environments for different type of testing. So DARPA used this as the platform to do the first spectrum challenge called SC1, which was inviting competitors to come and do some spectrum, sort of how to grab spectrum and compete with other people doing that. So this is an example of a test you can do. We are also doing MobilityFirst networking research experiments, which span quite a range of content distribution or mobility. Lots of different projects can be run on this testbed. And this testbed also happens to be connected to a global internet. You can think of this as an Internet 2 type of infrastructure with fully programmable nodes. And I think some of you may be familiar that in US we have a GENI project which has resulted in a programmable national network with about 30 to 40 nodes, I don't know the exact count right now, where you can set up routers in different universities and then run experiments layer 2 between the routers, and then you can run your own networking protocol on top of that. So that gives us the access to wide area part, and we have also contributed components to this has several edge networks are also built into the GENI testbed. Okay, so this is just a snapshot. I wanted to give you a sense of where I'm coming from, the kind of work that we do. And I represent about 12, 13 academic faculty and many experimental researchers who are staff scientists at the center. Ivan Sesker, my colleague, has been running a lot of European collaboration projects, including we were part of METIS recently. We're also doing OAI and many other projects, and I think OAI is also a project that India in particular has some involvement. Okay, so that's all about Winlab for now. Let me move into my main talk, which is about the 5G architecture and how we might be able to improve that. Now, as you know, there's a lot of talk about 5G these days, and part of it is an industry push with a heavy marketing flavor. But we need to set that aside and look at, okay, there's actually a future requirement, and it doesn't have to be in terms of 3G, 4G, 5G, that's getting kind of outdated. But I think wireless industry is reaching a point where they need to modernize the architecture and come up with something better. And the reason to do that is that many of these emerging network scenarios are very different from the telephony-oriented architecture which has evolved to where we are today with the wireless mobile world. So if you look at, in this picture, I've identified a few things. Of course, we all know that there's a heavy demand for mobile data which is growing, but there are also new application scenarios like vehicular networking, which I just mentioned. There's a standard called DSRC, which allows car-to-car communication between radios, between cars. Using DSRC radio, you can also use 5G, 4G to connect to the infrastructure and be able to support other modes of operation. Content delivery is, of course, a big area. I saw a number of slides as soon as I came, posters as soon as I came into links, which have content delivery networks, ICN, and so on. So the whole area of ICN or information-centric network has taken off mainly because of the large increase in content distribution and the demand it puts on the network. Then there's Internet of Things, which I know that many of you are familiar with that. The requirements for Internet of Things require, I think somebody, no. So the requirements for Internet of Things vary quite a bit, but one of the very interesting things is that you are trying to reach a very large number of devices, and yet at the same time, you don't care about all of them. There's only some of them with the right data or the right context that you want to be able to address and extract from. So there's a challenging kind of generalized multicasting or reverse multicast type of problems which we face. And then there's cloud services, which are, again, very mainstream for mobile users. A lot of mobile users would be lost without their Google Maps, for example. So there's a lot of services which we take for granted. So how do we provide those, provision those? And we need to look at the joint effect of edge computing as well as the mobile data itself. So these are all different scenarios, and we can discuss any of them in further detail. But one general observation is that if you look to where we are today with the 3G, 4G kind of network architecture, it's very far from what we really need. And industry has many strategies to approach that. And one part of it, some of the industry is thinking of clean slate solutions. So over here, I'm giving a clean slate approach, which is not very surprising, where we can realize that on the left-hand side, we have a picture of where we are today. There's a lot of legacy that comes from telephony. We have this MME, HSS, SGW, PGW, all these different components, which also happen to provide a lot of revenue for some companies that continue to make this type of equipment. There's no reason why the network needs to have this two-level architecture, which starts with signaling-based telephony protocols, which have been evolved under 3GPP, which basically set up IP tunnels using circuit switching, and then once the IP tunnel is in place, after that you use IP services from a gateway. So this gateway-based approach worked in the beginning, but again, it is not believed to be scalable, and as traffic increases, number of devices increases, the overhead associated with the IP tunnel-based approach is very high. Secondly, having two different network architectures which are joined together through a gateway is not always a good idea. You have no end-to-end semantics. Security is separate in these two domains. So it leads to many kinds of technical problems. And of course, for years, people have been saying that mobility is a standard feature that should be supported by the internet. And internet architects have provided previous solutions like mobile IP, parts of which have been adopted by the 3GPP. But the overall end-to-end architecture has never been completely revamped. So if you look at the right-hand side, the goal is to go to a mobility-centric future internet architecture which does not distinguish between edge networks and core networks and allows you to plug in any kind of radio access technology. Here, again, we use today different technologies for Wi-Fi and for LTE, and then when we combine Wi-Fi and LTE in multi-homing, we come up with yet another complicated protocol to do that. So the idea is that you don't need this, and people who have studied mobile IP 20 years ago, they knew that it's possible to come up with a flatter solution, but mobile IP had some difficulties. One of them is that architectural weakness, that it used only address-based routing, which we'll see more about later. But other than that, mobile IP would have been a step in the right direction, but then you still need certain services to deal with traditional 3GPP requirements. So we have to come up with a set of solutions that allows you to do everything people need to do from the service point of view. But all this without any tunnels, and should be able to route through this network to whichever ingress and egress point that you'd like to go through, avoiding any centralized bottlenecks or gateways. And again, if you talk to industry people today, one of the common complaints is the gateway overhead, the gateway headaches that most of them face. Okay, so what would a converged mobile internet protocol look like? Again, if you compare the protocol stacks, these stacks are these famous 3GPP protocol stacks, which have the GTP tunnels, and after that going into the IP world. What would be different now is that you would have a single, whatever you want to call that, next generation protocol, which is an IP plus kind of protocol, or a completely new protocol, whatever you'd like to call that, with a transport protocol on the two ends. And the only radio-specific part is the MAC and physical layer that allows you to plug in a radio and be able to connect it to its base station or access point. But other than that, you have a single protocol that works end-to-end. And this, of course, would simplify many things, improve security, and so on. Okay, so let's talk a few minutes about, I need to take this jacket off. Give me a second. So the architecture that we need should depend on the requirements that are associated with this network. So I think it's worth summarizing a bit about the requirements. So we spent about 2 years trying to understand the requirements of mobile internet. And at that time, we were also facing some skepticism from people in the wired network industry. They say, what is this mobility stuff? We really don't need it. That was about 7, 8 years ago. But today that complaint is gone. Most people are happy to have an architecture that supports mobility as a primary feature. So that is okay. But now we need to come up with a set of requirements. And it's one way to think about requirements is top-down. And what we did was we spent a lot of time going through all the different scenarios, looked at the use cases, and then tried to extract some common patterns from them. Vehicular, IoT, each has some different requirements, and once you go through it, it starts to become clearer. So over here, I'm just giving a few examples of the kind of requirements that we need to deal with. One type of requirement, which is the most standard one, is device mobility with variable bandwidth and so on. And we know, again, that end-to-end TCP doesn't work very well when you have disrupted channels. So that's one type of technique that we need to worry about. It's something that has been studied extensively for past 15 years. There are solutions out there that could be exploited. In addition, you have this issue of multi-homing. Most devices have at least 2 radios, maybe soon radios. There'll be 5 radios, and in future you'll have a software radio which can be virtualized, and you can run any number of radios on the same platform. So that opens up many interesting possibilities, and it's a fact that wireless has some channel impairments which wired networks don't have, but wireless has the huge advantage that it can potentially look at many gigahertz, maybe 5 gigahertz worth of spectrum, and be able to exploit all the signals that exist there. It doesn't happen today because we operate in a single radio channelized mode, but in principle, you could do more. So multi-homing, even with existing technologies like Wi-Fi and LTE or multiple LTE, can give you a lot of interesting capabilities. So this is something we need to keep in mind and see how the network can best support this kind of requirement. Another type of service that's interesting is vehicular. So vehicular involves some peer-to-peer ad hoc modes when there's no connection to the internet. We need to be able to support that. We can have cluster formation and local network forming and changing and moving. So you have network mobility is one of the requirements that we must support dynamic network creation. And the inter-network protocol, which today BGP doesn't have much support for dynamic transfer of network from one place to the other. Again, this is becoming quite attractive for many things like people who work with aeronautical platforms. They see the need to support Wi-Fi on every aircraft and so on. So some of this is becoming important for certain other mobility things, but this has an interesting element that the whole network moves and reattaches from time to time to different parts of the network. Another requirement is the content service. So again, this is familiar to all of you here. We need to build a network which is very efficient for delivering content, and ideally that content should be cacheable and should be distributed from the nearest location rather than from the original source of that content. Another requirement which I'm showing on this side is that of cloud services. So cloud service is an interesting case where you might want to access a cloud service near to you. So this is kind of similar to the Anycast requirement that has been discussed a lot in internet communities. And here we have a little bit more generalized form of Anycast where we'd like to be able to reach a cloud service which isn't overloaded or which has the appropriate services which I'm looking for. So that's a little more than just the networking cost in the path. And finally, on top, I'm mentioning that you have embedded IoT devices for which context awareness is kind of a central goal. So we must be able to identify what group or subgroup that we want to communicate with and query, and be able to get back the responses in an efficient way. So if I want to query the engine temperature of BMWs in central New Jersey, I can send out a query in some multicast fashion, but the reply will consist of 50,000 messages which have to be processed somehow. So there's a data aggregation problem also in IoT which needs to be addressed, and it would be good if many of these can be handled directly in the network. And the goal of future network designers should be to keep the network simple, but try at the same time to provide as many of these services at a higher level as possible, which we can, today, of course, IP gives you a nice lowest common denominator, and you can build a lot of overlay services on top of that. So that's the current network, and we need to, if we build something new, it has to be a lot better than that by giving you lower delay, lower overhead, and so on. But we want to be able to capture all these requirements somewhat transparently. Okay, so having gone through these requirements, we came up with a list, and I just want to share the main points of this. So we think that next generation network requirements will involve a set of functions. One set is security related, for example, providing authentication as a built-in service, data security, and so on. Some of them are provided by existing networks just differently. Mobility-related functions where you deal with endpoint mobility, network delay and delay tolerance during disconnection, having some awareness of the edge, especially important when we're dealing with multi-homing type of situations. Then multiple interface-related functions which involve some distinction between device names and network addresses, as we'll discuss further as we go along, but being able to, within the network, support multi-homing through bifurcation of paths and redistribution of the data on two or more paths. That's an interesting multi-homing type of requirement. Content and context support, I've mentioned already, that being able to name a piece of content and retrieve it efficiently, or being able to specify a context group and be able to reach it efficiently. Those are content and context specific, and they all involve some aspects of multicast. And possibly also in network caching. And finally, I mentioned that some applications do require in-network processing, such as media transcoding or cloud services, data aggregation for IoT, which I mentioned. So there are different reasons why it would be nice to have some in-stream processing capability. So this is the full set that we worked with, and the net outcome of this is that we're trying to go from today's IP service, which is a kind of a pipe-oriented abstraction, where you open a pipe to an endpoint and transmit data to it, to more general types of abstractions. And Francesco himself has done quite a lot of work on that, and I think you gave a talk here as well about that. So the service abstraction aspect is also interesting, that we are going away from the pipe abstraction to other abstractions based on names, typically getting a piece of named content or connecting to a set of identifiers which are prescribed through a context grouping and so on. So it gives you a much more general capability of dealing with content, services, and devices in the same framework. Okay, so with that background, I want to give you a specific realization of this architecture. So the idea is that taking all these requirements into account, we spent some time thinking about what would work, and there again, this was not done in a vacuum. There are a lot of previous work that we could look at. At that time, when we started the project about 7 years ago, we had access to some ICN literature. There was a very important protocol called AIP, or authentic. I'm forgetting the full acronym, but it is a Accountable Internet Protocol. Yeah, so that was a good piece of work that showed how you can build in security into every transaction, and so on. So we looked at all the different options, and we came up as a team with the idea of using named objects as the foundation for the next generation protocol. So here the idea is that a named object can be anything. It can be a piece of content, as we discussed. It can be a named context, a service, a device, an IoT object, and so on. And further, a name can apply to parts of the network itself. So any object which is connected to the internet will have a name, and we will use that name to do network functions such as routing or quality of service management and so on. All of these will be done within that framework. So that is the foundation, and we will show later how we can achieve that. Okay, so in order to achieve it, we came up with an architecture called MobilityFirst, and basically it uses named objects for, as we described. And the idea is that named object is designated by something called a globally unique identifier, or GUID. The GUID is a cryptographically secure key that is assigned to each object. And as I mentioned, that you can have many objects because the total number of objects connected to the internet is far more than the number of network addresses. So we have a scalability issue that has to be addressed as we go through the design. But the basic idea is that each name, so you could have 1 trillion objects, which are today we are talking about 10 billion objects, but in another few years it will be 100 billion to trillion. So you have potentially huge number of objects which all have to have names, and each of these names is represented by a public key identifier called a GUID. And today the length of that public key that we're using is 160 bits. It can be increased or decreased, but it's based on elliptic key cryptography, so it doesn't need to be much longer than that. But the recommendations from different agencies keep increasing that value. So that's a parameter that can be revisited. Now, once you have a name, the idea is that a device like this has a GUID, and then it can connect to multiple networks using multiple network addresses. So there's 2 levels here. There's the name, and below that there are network addresses. You can still use network addresses for routing if you like, but the primary routing identifier is still the GUID. And then once you go into the network, you might go through multiple paths, and you have inside the network what we call edge-aware interdomain routing, which is different from BGP, and we had to come up with a new solution for interdomain, mainly because today's interdomain doesn't support any visibility of an edge network. So we tried to deal with that problem and keep it simple at the same time. And then once inside the network, we have storage at every router. Actually, we use a concept of hop-by-hop transport and storage, and that allows you to do caching seamlessly. It also lets you do, and in fact, some ICN architectures also use roughly similar concepts where each router has caches a certain number of content and maintains some state for that. We also allow routers to do that. And inside the network, you can do content caching, and the routers have integrated computing and storage, which allows you to invoke functions of computing if necessary. So all this is supported by a global name resolution service below, which is the control plane. So this goes back to what I mentioned before, that it's nice to say, okay, we'll have names and route on names. The problem with that is that you have 1 trillion object names. You have to have in principle, old-fashioned router design would mean you have to have 1 trillion object table. But that we can address through different techniques, which we'll discuss afterwards. The basic idea is you have to have a name resolution service, which maps a very large. So DNS, of course, is a name resolution service today. And fundamentally, a name resolution service is the same thing, except that here we have to deal with a much larger scale with immediate resolution, in the sense of 10 millisecond is itself quite a high number. If you deal with certain applications require less than that, but 50, 100 millisecond might be okay for classical mobility, but we have to address that design problem. So these are the basic elements of the design, and let me now go into a few of the details. So the named objects allow you to create a number of different services which a user of the network can take advantage of. So you can still do a simple IP-like virtual link where you have a name of your destination and name of the source, and you set up a path between them. You can do things like service anycast, where you have a get to this kind of service over here. You can do multi-home devices by doing a send to the device name, and you can have options such as all interfaces or best interface and so on. You can have another kind of named content service, which is just to get something based on its name GUID. You can do, there's for content, context, multicast, or IoT query. You can have more complex queries like send to a context group, which is equal to taxis in New Brunswick. And somehow the name resolution service allows you to do dynamic mapping to that. So that kind of service will be attractive for IoT. And then in the top right-hand corner, there's one entry called late binding. So late binding is an interesting capability which had been proposed before. And it's something that allows you to go deeper into the network and make routing decisions later. For example, if there is a disconnection, you can do late binding to determine where a device has reappeared. So that kind of requerying from within the network is called late binding. And a late binding abstraction is that you can send to a network rather than to a device, and you can have the packet waiting to be delivered to whatever devices which are in that vicinity. And then finally, there's a pub-sub type of model, which also is enabled by this architecture. So these are some of the service abstractions. And if you look at the protocol stack, simple diagrams, we compare with NDN and IP. So the comparison with NDN is that in NDN, the content name is a structured identifier. It's not a flat crypto key. But it has some similarity in the sense that both of them can embody some ICN properties. So I'll go into that more. The GUID, although it is flat, it is an identifier that can be linked to the information schema, which can then be used to inform that service. The content name is a previously agreed upon content name structure, which is typically hierarchical and has some pros and cons with using that. So these are the three stacks. As you can see, IP is known to everyone. In the case of NDN, they have a concept called strategy layer or routing layer below the content layer. And in our case, we have routing below that. And we can also use IP routing below if necessary for compatibility. And on top, we have this computing layer, which allows you to plug in different kinds of computing services on top, and then invoke end-to-end transport outside from the 2 points, endpoints. Okay, so how does this actually get translated to a protocol design? So there are, in this, you have the top layer, which is this so-called name certification service. So we have some new services that have to be introduced to deal with names. And what was interesting is that when we decided to use GUIDs, which are public keys, we found that the probability of a collision, if two independent authorities would give out these keys, the probability of collision can be maintained very low. So given that, we don't require that GUIDs be coordinated. You can have a car company which gives out GUIDs for all its cars, steering wheels, everything can have a GUID. And that doesn't have to be globally assigned. So you can have many different name certification services which also embody the GUID structure. So within the name certification service, you can have some concept of a schema, and the schema doesn't have to be hierarchical. It can be graph or graph-like. And one of the problems with NDN, which has many good properties, is also that because of the requirement for a hierarchical identifier, it works well when the hierarchy of the content is well matched to the topology of the network. So if you have one location which corresponds to the root of the tree, and then you have many other locations which match more or less the distribution. So if you have a big company that can have this central down, but if you have a non-hierarchical data structure, and there are many, like Wikipedia is an example of a very non-hierarchical data where you can have pieces coming crosswise as a graph. So in those kind of situations, it becomes more difficult to use a structured identifier. So we feel that the flat identifier works well. We have a couple of papers that describe the benefit of a flat identifier and show, in fact, that it can scale better than a hierarchical identifier. In fact, the hierarchical identifier approach can blow up the total number of entries required at routers if the graph doesn't match well. Okay, so in our architecture, once you have these GUIDs that are assigned by name certification, they go into the packet header. And this is the central GUID service layer, which is supported by the Global Name Resolution Service, which is the, as I mentioned in the last chart. And then below this, you can have various kinds of routing layers. We have our own clean slate routing layer, which uses two protocols, one called the generalized routing protocol. And then the second one is the EIR, which is the edge-aware interdomain, which I mentioned. And we have here this notion of taking the GUID, maintaining it, and then optionally inserting network addresses which are available for routing if you'd like to do that, but you don't have to have that. The GUID remains the authoritative routing layer. And then you have, you can break these into different kinds of link layer packets and send them over. And we use, at least for our own data link layer, we have been using the notion of hop-by-hop transport with reliability on each hop. Okay, so to see how something like this works with the different layers, we can think of it in terms of three logical planes. At the topmost layer is the meta information layer, or you can almost think of it as an ICN plane. And then going below that, you have the GUID service plane and then the routing plane. So you can see a simple example here where we have my slides are for project 1 happen to be stored in FIA project 1 are stored at both Rutgers and MIT through different kinds of schema. So this is an example where you have somewhat of a graph-like schema where both Rutgers and MIT maintain the MobilityFirst set of content. And these slides are tied into that, but it also happens that NSF has the same file because we sent it to them as a project report or something like that. So these files can be cross-referenced in that way, all in the information plane. And within the information plane, there is the GUID assignment, which allows these slides to have a very specific GUID. So the slides in question have this GUID over here. And MIT has a GUID for its server, and Rutgers has a GUID for the server, and so on. So each of these entities, whether they're a server or a mobile device or a PC or the content, each has its GUID, and they're logically linked through this top plane. Once you have this logical organization, after that, there is a simpler process here in the GUID service layer where this device has a GUID which wants to get segment number 2 of these slides. So it is able to fetch that segment number and just does a get GUID once it has that value as part of the application discovery process. And it does that and then sends down the network addresses, and routing can now be done between this user device. And it happens that by anycasting, this cache is closer than MIT server or Rutgers server. So it fetches it using anycast. The get is intrinsically an anycast function. So once it does a get GUID for that segment of content, it just fetches it from the nearest available GUID in the among those which have that piece of content. So all this information, of course, has to have the GNRS over here. And this is called the Object Resolution Service. This is an additional service that allows you to map, to do like a Google search type of things on named content with human readable names versus their GUIDs. And this one goes from the GUID to the network address. So these are supporting services that are needed for the architecture. The ORS is not a critical service. It is, you can think of it as a application-specific service. But the GNRS is a global generic service that applies to all applications. This is another example of how an IoT example might work. So again, the information schema is all in this top level. So here you want to change the temperature at Bob's home. So Bob has some GUID corresponding to his environment, which includes the home, the kitchen, and so on. So there are a lot of different devices which are tied in through the yellow arrows there. So you have to access them in the logical way as specified over there. But once you have that, this all maps down to GUIDs, and in this case, there's a message that needs to be sent to Bob's environment, and this can be mapped into a very practical routing plane, which has the job of taking that address and mapping it to a network address, forwarding it. One interesting additional thing we show in this diagram here is that you can have a IoT gateway as well, with something which we call a GUID to LUID translation, where you have a lightweight device which doesn't necessarily support 160-byte headers, 160-bit header, so we can simplify that process. So this is an example of that. Okay, so these are some high-level discussions about how the protocol works, and let me from that move on to some of the technology components that go into making all this work. So the first technology component, and most important one, as I mentioned, is the idea of name resolution. So this is just recapping what I already said, that you have different kinds of naming services, which then come up with a globally unique identifier, which then feeds into a global name resolution service, which supports routing below. Okay, so the idea is that you go in with a GUID, you come out with a network address. So before, I'll give a couple of examples. So this is early design that we did for something which we call Dmap, which is a global name resolution approach which uses DHT techniques to store throughout the network. So here the idea is that all networks in the internet will share between them the task of maintaining this large global directory. So we do that by assigning, by taking a hash, a set of known hashes h1 to h2 to hk. In this case, we show IP as an example. So if you have a GUID value of 10, these hashes may result in the following IP addresses. So if you had an IP network, what it would do is the user which is trying to update this value of 10 will then find its way to 67.10 to 44.3 and so on, .32 and so on. And the idea is very simple, that you're just taking a DHT approach and using traditional techniques from peer-to-peer networks, which have been studied quite a bit for the past 10, 15, 20 years. So using this technique, effectively what you have done is you have reduced, if you take K storage locations, each router is storing only one divided by n of the total number of names. So if n is the number of networks equal to 1 million, then you effectively distribute these trillion into 1 million each. So effectively, each network is maintaining about 1 million entries rather than trillion entries. But of course, there's a penalty to be paid. And the penalty here is that you're doing a DHT lookup each time you need to resolve a GUID. So the GUID resolution certainly has to be done at the edge of the network, but it may also have to be done inside the network depending on which routing algorithm you're using. So if you're using late binding, then inside the network, some router somewhere will also need to query the GNRS. So for that reason, we also, after doing this work, we decided to look at more optimized name resolution services. There are 2 of those that came out of this project. One of them was done by my colleague Arun Venkatramani at UMass. It's called Auspice, and I think the Auspice paper appeared in 2000 and which, do you remember which, 2014 in SIGCOMM. And then there's another design that we did at Winlab called Gmap. Both of these effectively show that with some amount of local caching and placement. In the case of Auspice, he did very careful placement per GUID. In the Gmap article, we showed that you don't need to do per GUID placement. You can do kind of aggregated placement based on locality and region. And using that, you can bring down the latency very significantly. So here we see that latency was in the order of 50 milliseconds without any optimizations. And that was improved to about 10 milliseconds and below in the more optimized scheme. So the net result is that we are able to show some kind of feasibility, whether or not it will work at internet scale. We need to do more practical work, but at least from the point of view of simulations and detailed design work, it has been proven that you can get up to this scale with low latency. Okay, so a second piece of technology that we use is called the Gstar, or generalized storage aware routing. So this is a derivative of some of the ad hoc network protocols that came out in the early 2000s. We ourselves worked on some of them. And one of the basic ideas here is that we want an architecture which supports seamlessly, will support highly disconnected to fully connected, and still there should be no major performance penalty. So it was possible using a variant of OLSR. We came up with a two-level kind of routing, which has the two aspects. One is the intra-partition table, and the second is the inter-partition table. And then we can combine DTN and ad hoc network aspects. And it doesn't look like an ad hoc network if everything is fully connected on this side. It's fine, and the protocol as a baseline should work well for that. So one interesting thing that we talked about was this notion of measuring both the short-term and the long-term link quality. So in the edge networks, we found that you can get a lot of benefit by distinguishing between these two. So what you have in a volatile network, the short-term path quality might be really good and long-term might be bad, which then means you should try to push as fast as possible. If the short-term quality is bad and the long-term is good, then clearly some type of storage can be helpful. And the routers themselves have storage, so the routing decision that Gstar uses is essentially that each router will look at the relative long and short-term path quality, and if it's here, it will store. If it's there, it will forward. So it's a very simple technique, and it seems to work very well, and we were able to show good gains in a variety of practical scenarios. Another little more complicated topic is that of interdomain routing. It's nobody's favorite topic because no one wants to touch interdomain, and researchers in general are very reluctant to get into that. We don't want to make big changes, but we did discover that it's very difficult to do anything with BGP with what we had in mind. So we came up with a proposal, you can say, and we are still thinking about how it could be gradually deployed. So in an edge network like this, what we are recommending is the idea of using A nodes and V nodes, where an A node is a aggregated node which the user would be willing to, the owner of the network is willing to publish and expose. So rather than just having a domain as a single entity, the domain can expose certain amount of internal topology. So in this case, this domain is a big one, and it might have benefit of showing several ingress and egress points. And it can then optimize its own traffic management and many other benefits that come from exposing some of the internal structure. So we have here some concepts of using virtual A nodes and V links, and then interdomain routing protocol is basically uses a OLSR type of link state protocol and distributes that, but it does so with a telescopic routing function which reduces the amount of overhead as you go far from the network. So if you're 1 hop away, you send at a certain rate, 2 hops, 3 hops away, the rate is reduced. In that way, we can manage the whole, yeah. So we can manage the overhead and then get very interesting, good properties if we can build an interdomain of this sort. So the router in MobilityFirst that you need then has a structure which is not completely different from IP today, but if you look at it, it comes in with a GUID. SID is an indication of the service that you're trying to deliver. So it could be multi-homing or delayed delivery and so on. And then these network addresses are appended on as available. So it might be for a non-mobile device, you can attach the network addresses at the sending point and then send it out. and it goes through the router. So you see over here, the router has two kinds of tables. There's a more conventional network address to port table, which is like a forwarding table in IP. And here you have the virtual or slow path, in which you have to look up the DHT in order to resolve the GUIDs where necessary. Hopefully that doesn't have to be done for every packet. It is done strategically based on when it needs to be resolved internal to the network. And then going out, we have an intrinsic multicast structure, which in this case, there are two paths that correspond to these two network addresses, NA99 and 32. And you can see that the packet is now split, where the dark blue address is appended here, the light blue is on top. So you have to do like you have to take out the pop and push the headers and then create multicast copies that go out on different paths. And you'll see later how this works easily for multi-homing and so on. So let me just give a couple of examples. So for handling disconnection, for example, this slide shows that you send out using a given GUID, and the SID is indicating that you want some kind of delay-tolerant delivery. So here the SID is mapped to NA99 initially at the edge of the network, and the NA99 is inserted into the packet. And that's because you got the GNRS lookup told you that it's at NA99. After that, it moved down to NA75 with some period of disconnection. So what happens here is that it starts being forwarded hop by hop. Each router will look at the destination. If there's a delivery failure, then the router at the edge of the network will store, and it sees that there's a delay-tolerant delivery requested, which means that I need to late bind. So which allows me to store and then look up again. When the device reaches NA75, it will then update the global name resolution service, and the periodic queries by the router will determine that it is now at NA75. So this router over here will rebind and will put the new address of NA75, which is the dark blue address header here, and deliver that to the mobile device, which is here. So this is a simple example for disconnection. And we have, again, for each of them, we have done a lot of results, both experimentally and analytically. So this one is a simulation result. One of them is a trace-driven simulation that shows two examples of how this protocol compares with TCP/IP with different parameters. This is for host mobility, and you can see that you can get good improvements, mainly because of the routing protocol over here. The network mobility example is for buses traveling in San Francisco, and you can evaluate the interdomain routing protocol to see some improvements that can come through the late binding and interdomain principles which I outlined. Okay, and I'll be happy to send papers for any of these topics, and I can post some of them up for you later. So this is another example of how to use this protocol to do dual homing. So in the dual homing service, similarly, we have a GUID that says I want to send to John's laptop, and John's laptop has two interfaces. The two interfaces are separately updated on the GNRS. So if you look up this GUID, the GNRS will return two addresses, NA99 and NA32. So then I'll put these two, NA99 and 32, into the packet and then start forwarding it through the data plane. When it reaches a bifurcation router here, some router will look at this and say, okay, it makes sense to, because the two paths are divergent here, it makes sense to send them out separately as a multicast over here. So you split and send to the two. Now this need not be a multicast. If it's to all interfaces, it would be a multicast. If it's an internal in-network supported multi-homing, then you can have a policy like 50% packets or based on some signal quality metric and so on. But in either case, it is network-assisted multi-homing that's being realized. Okay, so that shows, and these are some results that again show that with this protocol, let me talk about the second one. This is a test done with signals which were collected over Princeton. This is our office here in Winlab. And this is going down to Princeton along a highway called Route 1. So there are two networks, cellular networks, both giving AT&T and Sprint, which were both measured. And then using that, we could see that going down this route, you get decent signal in most places, but somewhere one network is not so good, the other is better, and so on. So we have this red bar corresponds to the performance of our protocol. You can see it achieves about 35 megabit per second as compared with MTCP, which gives you about 24. And if you compare with single interface, it's almost double the single interface throughput. And this is a simple byproduct of in-network. So I think I saw somebody's poster outside about in-network multi-homing. So I think somebody here has also been looking at that problem. But this is a good example of where being wireless allows you to collect signals from multiple networks and achieve higher performance. So when we talk about 5G, we can get 100 from one, 100 from another, but in principle, you could get 300-400 megabit per second peak rate without having to make the technology that much faster, the radio level. Okay, so I'm going to skip this one. We also recently worked on a multicast concept that is based on GUIDs, and the key idea behind that is that multicasting today is not easy to do or efficient, mainly because we have a lot of setup procedure, and most of the existing multicast like PIM-SIM has a significant overhead for setup. So we can cut that a lot by using the GNRS, which has a relatively low overhead for lookup, and use hierarchical concepts within the GNRS to define the tree. So in this case, if there's a tree which looks like this, you can map GR11 to GR21 and GR22 and then GR22 and so on. So the GNRS is not only a name to network address lookup, but a very important aspect is it's a name to name lookup as well, which can be done recursively. So recursive use of GUIDs gives you a lot of interesting properties and capabilities that deal with things like context and multicast groups and so on. So this is a recent paper. Again, I can refer people to that. And again, here we show that the comparison with PIM-SIM is quite good, and as the size of the multicast tree grows, you can get significant improvements in the overhead associated with the scheme. Finally, I just mentioned mobile edge cloud. So I know that Francesco has already talked about virtual networks somewhat here. So the idea of mobile edge cloud is that what we'd like to do is be able to do routing to the nearest cloud. That's a fairly simple concept, and that's anycast. But if you want to inject some application level properties, one way to do that would be to create what we call a virtual network on top of the standard MobilityFirst. And once you have a virtual network, you can put customized metrics into it, and we call that approach application-specific routing, or ASR. So in the ASR framework, the basic idea is like this. You can have any given topology, and then you can decide what your this virtual network's topology is going to look like. And similar to previous works on virtual network, there was a project called GENI at Princeton University where they did overlay architecture where you can specify topology and quality along the virtual network. So we're trying to achieve the same thing on top of native support in MobilityFirst using only the global name resolution service. So what's different here is we don't create a separate control plane protocol to support the virtual network. Instead, we use the existing service provided by global name resolution service to create effectively a virtual routing table at every router. And Francesco has already spoken about that, so I'll skip that topic and mention that this worked really well. And we did some experiments that showed, for example, this type of network, which is a simple testbed that we set up with a Japanese group in NICT. And we are able to show that for real-time application queries, we can significantly improve the percentile response times by following this kind of approach. Okay. So that's basically what I wanted to say about the protocol itself. I know that we're well over time, so let me just try to wrap up here. As I mentioned in the beginning of my talk, that we have a strong methodology for doing test beds and scalable experiments. This is a chart that shows the methodology that the project has followed so far. We have done quite a few evaluations of the protocol using NS3. We also did quite a lot of laboratory testing inside Winlab using the Orbit testbed. We have done some outdoor testing using what we call an open programmable base station, where we can set up these protocols running on a clean slate network with fully programmable routers and fully programmable base stations. And we also have been doing some real-world application trials using the GENI testbed. Real-world is limited in the sense this is only users that we are able to find, but not commercial service. There's a talk in US about a power testbed, which has just been announced recently by the NSF, which is a big project aimed at building 2 city-scale testbeds which use advanced wireless in a fully programmable way to allow people to do experiments either on the radio or on the network or both. So that's the goal. And so we have been pushing up this side, and we have done these tests and these, but not at huge scale. This would give a lot of scalability where we would have potentially thousands of end users and a citywide deployment, for example. So that's something we'll see where that ends up, but the process has just started. And in 2018, NSF will be awarding 2 teams projects to build this kind of outdoor large-scale test beds. We have been using Click software routers, as I mentioned earlier, SDR open base stations, and the deployment on GENI looks something like this, where we maintained about a 7-node network for quite some time and used it to study many of the protocols I outlined: multi-homing, named content delivery, in-network compute, context-aware services, and so on. And these were some of the sample demos that we gave at different events in the US. Most of these were at GENI engineering conferences, where we were able to show, for example, an example was video delivery with in-network transcoding and mobility that can be shown, and a lot of different services you can set up once you have this. And we're working with a satellite company to use named content distribution, CDN, very simple type of concept, but it was attractive for that company because they didn't have a network before that. Okay, so in conclusion, I just want to say that this is a particular research architecture. It has its results, and we can give you the papers for different details. I think the general learning from this is that we believe that you can get significant performance improvements with a better clean slate architecture. We realize that standards committees, other things have to be involved. So today, actually, there is a process going on in IETF to try and restart some identifier-based architectures for mobility, and this is tied into some ETSI initiatives called NGP, for example. And so if identifiers can be revisited by these committees, we can at least start with IP routing and then build identifier-based end-to-end protocols. So there are many benefits that one can get from that. And we think that with evolving architecture, we are at a point now where we not only need to think about network architecture, but about the realization in terms of software-defined components like SDN and cloud. And we have been thinking about how to integrate edge cloud, and that's some of the future direction in all of this. But very important to all of this is to maintain modularity, let the base stations just plug in and the radios, Wi-Fi, and so on, and then build a clean network architecture which supports all of these things going forward. So that's all today, and I'm sorry for going over time a bit, and it's very hot in this room, as we know. So thank you for your time, and I'll be happy to take questions now, plus I'm here for some time.
Can I start?
Sure.
One thing that I didn't realize before, I'm advantaged to know a lot of his work, so is what happens if we start with the GUID of 160, and then at some point the system explodes and we need the 256. Unless you use the same function, that is unlikely. All the IDs of 160 are no longer matched. Basically, for the same ID, you will find another object. How have you ever thought about doing the transition?
Yeah, so that's a success question, right? So if we're that successful to have
Is the IP question?
10 million,
Is the IP question?
10 million users. So I don't know the answer to that actually, but I think, from the point of view of routers, the technology that we think will be used is fairly programmable, and changing the routing tables and the router software shouldn't be a big problem. But as you said, if there's a legacy set, but GUID assignment is not a big deal, so you're just coming into it. So if you have a pre-existing GUID, you have to go and get the new ones. So, and there's no reason that people are attached to them because they don't mean anything, right? They're just some bit string. So you have to update that. So the simplest answer is you would have to go get your new GUID at the time of transition.
Everybody in the network to readdress.
Right, and there can be a way to do this that it can be done by the router, not by the endpoint. So the edge routers can also take on that responsibility.
Is there any reason you can't have variable length GUIDs?
No, I don't think there's a problem. I have to think about that. But we were thinking a lot about just keeping it simple enough that it's a fixed length.
How do you authenticate them?
Yeah, so
if I give you a random string of bits, how do I know it's a GUID?
Right. So you know it's a GUID only if you can ask for a query response protocol by which the person can sign it also. So there's the public and the private keys that can be used. Right. So if somebody sends it to you and you doubt that that GUID is a valid one, you can ask the person to sign it and send it back.
How do you ask them? I'm just kind of curious because this sounds like a prime denial service attack in the making.
Yeah, we have
non-existent names in the DNS are one of the classic ways to attack it. And so if you have to have some way of authenticating GUIDs.
Right. So the GUID, when somebody is sending, so if you have a DOS attacker who's using a GUID, so the GUID itself is not the problem. The question is whether that person is trying to mount a DOS attack or not. So if there's a DOS attacker, you can identify them through the GUID and then shut them down. The GUID can be traced back also to its name certification service, but there's always the ability to do a public key, private key protocol to find out if somebody is a valid user. But you could also have a valid user who decides to mount a DOS attack.
Well, aren't you going to need some kind of hierarchy to be able to figure out how you authenticate?
Hierarchy of what?
Of certificate authority. It's like certificate authority.
Yeah,
like
right. So it is exactly like the CA authority
thing. So you
thing.
have that on top?
You have that on top, except that these are not necessarily in the same hierarchy. You can have a CA authority for devices, which is hierarchically structured, but you could have a different one for the car companies. So we thought it would be a good feature to allow them to be independent of each other. But yeah, you can trace things down with the CAs.
Do you give consideration to business issues? That's something that seems to be missing in what you've described up to now.
Mm-hmm.
Who makes money from this network and how? I mean, are there content providers like Google? Are they going to cooperate? They'll allow their content to be stored anywhere and retrieved? Or surely you have to inform them?
I think that's a good point that you're bringing up. So far, this has been more of a protocol design and verification project. But in terms of how to incentivize it, there are a few different things. The name resolution service is a shared service. So we have looked a bit at what are the incentives for networks to cooperate and provide this global name resolution service. So that's one aspect. If a network is rolled out, then you have to have appropriate business incentive for service providers and users to want to use it. So
when you have multi-homing, when you said Sprint and AT&T, they're not going to just nicely cooperate. So
they actually don't need to cooperate right now, because all I have to do is set up a service. So this can create some new business opportunities. So you can have a aggregation service provider who promises 100 megabit wherever you are, and it's based on but Sprint and AT&T don't necessarily have to cooperate. Of course, they can get really nasty and cut off the connection whenever they discover that you're doing that. It's possible. So there are some such issues, yeah. But I think the big picture is that if you provide better services at lower cost, then people will have an incentive to join.
But not if they don't get money, like if Google can't sell its publicity, its advertisements and its content, and
I don't
know
think
what its users are using and what they're doing.
I don't think
so
that
they
needs
use
to
this as
change.
marketing.
You can always have a logical structure in which my PowerPoint file is always associated with some advertising that Google provides.
Well,
right?
that doesn't want that, does it? It wants different ads for different people.
Yeah,
you know?
yeah. So that whole inserting of ads which are relevant, that we haven't done a detailed study of that, but that can be done very nicely with this kind of named object framework. Because with each named object, you can associate a set of other objects which could be Google ads.
Yeah, but you have to communicate with a content provider all the time, and that sure is as heavy as protocol as the other ones.
So no, I mean, you don't actually have to continuously communicate with the content provider. So at the time the content is named and generated, at that time you can associate some ads with it. So yeah, I mean, you might have, but we haven't studied that problem in detail.
But ads are associated usually with the viewing user as opposed to the content.
Yeah.
So that doesn't work.
Yeah, but I'm saying that at the time, so there is at the time, say, there's a piece of content that some content provider is putting out. There's a third party like Google who is going to insert the ads for that. And those ads are user specific in the sense that I have been looking for cars, so they want to insert a car ad. So as soon as you see this combination appear of A wants to send to B, then that kind of, in this case, the user is pulling the content. So at the time the user pulls the content with that GUID, Google, there are many opportunities for Google to insert. So either way, it can be pushed or pulled content.
It's not new. It's not simple. I mean, sure. I mean, anyway.
Yeah, so it could be simpler, but I would have to work through the details to see what you have in mind. Yeah, we can chat about it afterwards. Yeah. Yeah.
I have a question about the distributed, so the resolution of the name. You said that the latency for name resolution is not so high, but do you have also some figure about the time to update the table? So in that sense, it's arrive a new, how you call global identifier.
Right.
I want to update the table. How much time I need?
Yeah. So the update was about.
Is an issue or is
It hasn't been an issue so far, but for certain services, you can see why that needs to be kept really low. But of the order of 100 millisecond to 200 millisecond is what we're getting right now. Yeah. But certain application may require that it should be very fast. Yeah.
Because for DNS, you take a lot of time to update the table. Here, you cannot.
No,
wait
yeah,
so much
yeah.
time.
Do you have an idea how the existing operator networks can migrate to this kind of architecture?
Yeah, so
How difficult is it?
I think as you could see that our focus has been on the 5G edge network. And although this was started as a general internet architecture, making the internet change inside initially is harder, right? So you probably want to start with an edge network, and a lot of operators are now saying that they're open to the idea of a completely different mobile edge core, the core, what they call the mobile core. So that part is really is likely that you will see many new solutions or basically clean slate solutions there. So we have an opportunity to put it in there. Now, once you start putting in multiple of these, so if you just have one edge network, then it doesn't need a global name service. It can operate with a local name service. So it's like a local DNS. But if you now start adding multiple edges, then they want to talk to each other. Then you can start introducing some of these inter-domain capabilities. But it's a slow process. Yeah.
Thank you.
It's very hot in here.
Yes.
Okay, thank you for your time again.